Okay. Good afternoon. Yeah, I'm from Beijing Normal University. So you what is the yeah this yeah. In fact, I'm not astronomist. That I'm my major is the computer science. Now I work at the School of System Science in Beijing Normal University. But this is my lab mainly for image processing and pattern recognition. Okay. So in this talk, we just briefly introduce about current work ongoing. So because as a principal, I hosted a project from Natural Science Foundation of China, and this is a joint project from Chinese Academic of Science. So that work for the data processing for LAMOST. So that say the Professor Scott just give a brief introduction about the LAMOST. Yeah, LAMOST is a larger scale array multi-object fiber spectroscopy telescope. So yeah, so this is the light flow like the here. This light is object light plus sky background light. Then with a mirror is Smith spectroscopy. Then send to the I think this is the focus plan. Then you with the fibers send to 16 spectroscopy, and each spectroscopy have two CCD chips. One is for red, another for blue. So all together, there are 32 CCDs. Yeah, this is the LAMOST focus plan. So altogether, 4,000 fibers divided into 16 region. Each region we have 250 fibers. Then this is for one spectroscopy. So in CCD, we say the two-dimensional spectroscopy. So that's a symbol like this. I think yeah, the 250 fibers and bounded to the slate of the spectroscopy. So it may be this is the bound maybe 25 fibers bound one group. So this maybe this is the gap between fiber groups. So just like this. But though our task is to deal with this two-dimensional CCD image, and here is the flow chart about the two-dimensional pipeline. So we here we can see here. So we need some phase to calibration, to calibrate. This is for arc lamp. So also this also for flux calibration, or this also for for the hardware of CCD to eliminate some noise. Also, in the object file, also is a mixture with the sky light. So we need the image recursion. So there are several steps to deal with these images. Here we can see there's a sky subtraction. So from sky subtraction, then also doing some things about the flux calibration, or also get the flux. Then also, yeah, this part also have to do some PCA sky subtraction, and get the final spectrum. This spectrum and will into to one dimensional pipeline. The final get the spectrum data and release to public. So we are mainly focused on the two-dimensional pipeline, and in this presentation just for the sky subtraction problem. Sky background, yeah, you maybe better know than me, so we just skip this. So okay, we see the related work. So for the LAMOST system, the image modeling like this. This is observed image, as the CCD image. So is related with this is source. Yes, objects light. This is the background for the instrument. This is also this is the noise. This part will be sky light. Sky light include continuous spectrum plus emission line in the sky signal. So here, that's for image modeling. So we use this to express the PSF point spread function matrix. Like this is the model. So we main concern here so how to do sky subtraction. So doing this, we need to modeling two-dimensional sky background. Currently, currently in the LAMOST, the data are released. They just use one-dimensional sky model. Use two methods. One is use simple sky method. This simple sky method is just use the 10 sky fibers. Yeah, this is 10 10 fibers received the sky signal. Then average this 10 become one sky signal line. Then use the B span to fitting this line. Then all the other can be considered the objective signal plus sky signal. So use this as the subtractor to eliminate the sky signal. Another one is for principal component analysis method. So the advantage in one dimensional sky subtraction, if we use the super sky, that is because it's the average of 10 sky signals. So maybe it's stronger techniques to abnormal flux. But the disadvantage is that the fitting process is a normalization operation. Then super skylight cannot actually characterize the defective within a sky background. If we use PCA method, the PCA method that also maybe can get the main command of a main command of several operations, but this not consider the spatial variation about LAMOST. You see with from focus plan of LAMOST, so you just basically assume that the is the uniform, but in fact the sky will be very slow variant in such a larger in the larger region. So now we are consider the two-dimensional sky subtraction technique. This is our new approximation through self-similarity optimization method. As we know, this CCD image contain 250 signals. Maybe there are 10 fibers that received the sky signal. Other than the operative plus sky. So we just use the parts of a sky signal and want to eliminate the whole image sky background. So this is very maybe a little difficult. So you just if you use one average like a silver sky light. So maybe here maybe either the maybe better match the sky background signal, but in the this part maybe is maybe with a little difference. So how to make the better application to eliminate the sky background signal? So I think it's a very difficult problem. So now we just try to use some image processing method to do this. So like this step, you track the 2D spectrum and inside the sky background running a self-similarity guidance algorithm. That's the step to doing such work, but I think this work is done by one of the master students. Is a background. Her background is commercial. That uses the image processing problem. This is considered as the pixel image. So not the physics meaning for the sky. You with this the self-similarity with one skylight is similar with a neighbor, and just consider the small variation. So that get this model. Yeah. So this is for different that get the from several pixel, then and expand to more pixel, then expand to whole image. That's the idea. So yeah, this result is current going is not good. So this is just the now maybe also need a lot of problem we need to solve. Last one, I will just say the this. So currently maybe you saw some words is confused about the different field with different terminology. So now most of people say that artificial intelligence also the deeper learning, but artificial intelligence is not merely deeper learning. Yeah, artificial learning astronomy. So most match the words is computational intelligent astronomy. We just finished a survey paper. You can read this. Maybe you can find some work of yours, or maybe find some method you can apply. Thanks, Phil.